So combining these two, it seems all I did is still some intuition plus some algebra. So as a second year paper, I think it's still not that good. So that's why I included the binary one. So moving on to the binary one. So the version that I had before for the 4060 one, I had that convexity conditions. So in order to so the first thing to think about when we think about binary cutoff rule is some kind of convexity condition. So if the difference is convex, then it works. But then that requires this stochastic process to be able to preserve the convexity when taking conditional expectations. That's not so, as suggested by Professor Damiano, that's not going to work for most of the common stochastic process, like the additive and multiplicative ones are not going to work. They will not preserve convexity, so this is not feasible. So I'm basically all I did is prove something. If some condition that never holds, then something happens. So that's not useful. That's why I removed that part, and I cheated a bit. What I did is break this into two parts, like this. So another way to get the cutoff stopping rule, binary cutoff stopping rule, is we have two types of allocation. So one type is decreasing, the other type is increasing, and then the max of them will have that kind of concave convex shape again. So we should start with thinking about only two actions. So one action has decreasing utility in the valuation. The other type has increasing. The other type is has increasing utility in the type. Then we have exactly this structure. Then if we add on other things to it, the way to do this is, of course, using static mechanism design on both sides. One is decreasing and the other one is increasing. So formally, it's like this. We have two types of allocation. One is the minus one and the plus one. And for notation simplicity, you don't really need to do this. I call the plus one just the positive Q, and I call the minus one the negative Qs. So then they would combine to form some kind of interval, such that because we can only choose one of these two types, I mean one element of these two types of terminal actions. So I don't want it to be like from 0 to Q and another 0 to Q. Then we basically combine this interval to have minus part and plus part. So that's why we have a notation like this. And then the sufficient necessary condition looks the same actually. We have the Spence-Murley's condition still, one of them being increasing, the other one being decreasing, and the Pavan-Siegel-Toykas condition is the same as well. Just one is smaller, the other one is larger. However, the proof is different. So I will do the proof first, and then I'll give the example. I mean, I didn't even state the theorem. The theorem is exactly the same, except for I changed the single to binary here. So these two conditions are satisfied if and only if all of them are implementable. So the proof goes like this. So the Spence-Murley's now would imply two things at the same time. One is Q is implementable. The other one is the monotonicity of the utility after we implemented the terminal action. So the capital U is basically after we choose the optimal one, what kind of utility do we get? Of course, subtracted by the prices. And the second thing I do is the same. It's the same as the single cutoff rule. Each one of them just individually implies some Z being increasing or decreasing. I will show you what those Z are a bit later. So moving on to the next one first. The next one is different. So in order to prove that U minus V is decreasing or increasing, because you know that these two parts are the same, so the V part is the same, and we need just two different functions subtracting the same thing. One of them is increasing, one of them is decreasing. So this U must be powerful enough such that it overpowers whatever the direction is for the VTs. So only Z minus being decreasing here it's not enough. We all also need u minus to be decreasing as well. So now let's see what those things are. And I'll give a simple example. The one with multiple q's on both sides is very complicated. The the expressions are very complicated. The idea is not complicated at all. So U minus basically means the utility of obtaining the minus the minus allocation minus this price, and U plus the same. The Z is the next period minus this period. So the only thing you should notice here is that this is the utility from the minus 1 allocation in the next period subtracted by the minus 1 allocation in the first period. So this set is not really the marginal incentive. The real marginal incentive should be something like this. It's the max of these two. Subtract only one of them. So the good thing is that that one is stronger. That one actually implies the one below. So in the prices, I actually have this. So the way to construct the prices, we need these two objects. So these two max minus individual one type marginal incentive. And then if we have the one on the top, then it can actually imply those works as well. So that's the good thing. And then because those things are stronger, then we use them in order to prove the monotonicity of U minus V. So the idea basically goes like this. If this using overpowers the next period's U part, I should probably give an example. So if the U minus overpowers, basically dominates in the sense of slope being larger, if U plus dominates U plus in the next period, and of course it dominates the U minus because it's negative. So it dominates the whole thing. So that's the idea of why Z plus would imply that marginal incentive being monotonic. And because it dominates the previous one, which the previous one dominates the previous one, so the current one dominates two periods before as well. So that kind of thing is done by induction. Because I'm only choosing once, so I don't need to overpower the sum of all those things. I only need to overpower one of them in the future, and it's kind of each one I'm overpowering the next one. So if we stack those things together, we can see that actually works. So whatever V is the max of all those future ones, and this current U being dominating the next one dominating the next one, we will have, if we stack them together, the current one will dominate all the future ones, so the current one will dominate V. So that's why we have U minus V being decreasing. So that was the intuitive idea. In here, then we have the similar proof to the single cutoff rule, so it's the same. And then I will not spend much time on the converse. So the Q implement will imply two things at the same time, and then this thing goes back as well. And the thing is that if Z does not imply that thing cannot go back to imply Z being decreasing as well. So we need to combine this with the U minus thing. The U minus monotonicity of the U minus combining with the U minus V being decreasing, then we can go back to whatever that Z monotonicity is. And then we go back from Z to U the same way as we did in the single cutoff proof. So now going back to the advice example from slide 3, we have the unknown state, and the agent has a private information, which is the belief. Then the additional assumption we need is X forming a martingale, and the utility function is linear. So the CT could be a sum of all those things, but I just didn't write that. But the important thing is that they are linear. So one slope is alpha, the other slope is beta. So given those conditions, I'm just repeating the assumptions, then all of the binary rules are implementable, and we have some closed form formula for the prices. So the proof is basically observing that if any function is bounded by two constants, then the Martingale plus monotonicity transition property would preserve that thing. So if V is bounded, then expected V to the previous period would be bounded by those two as well. Then if that condition holds, then we have the Z condition hold, and then from the theorem it works.